Hello, my name is Jordan Smith, and today we'll be talking about velocity, or more specifically, constant velocity. We'll be doing this through videos, a few fundamental principles, and models through the tracker software. Before we start, we must ask, what is constant velocity? Constant velocity is achieved when there is zero net force acting upon an object. As stated, velocity would have to stay the exact same within the given time intervals. Here is a screenshot of me using the tracker software to model the ball moving across the surface for about half a second. Over on the right, you'll notice the position versus time graph that tracker has provided, and also on the bottom right, you notice the data that I've been able to collect. With the data provided on the bottom right hand corner of the screenshot that we just saw, we notice that the observation start time was at 0 seconds, the observation end time was at 0.55 seconds, and that the ball's initial position and initial velocity only play a part in the x component, with the ball's initial position being at negative 0.103 meters and the ball's initial velocity being at negative 0.882 meters per second. Now, we're about to create our computational model. Located here in lines 34 through 36, I was able to place the ball's initial position vector and the ball's initial velocity vector, which we explained in the previous slide. I've also placed the ball's initial time, and I was able to calculate our delta t, our time step, which I found to be 0.017 seconds by dividing 1 by the video's frame rate, which in this case was 60 frames per second. I shot it on my phone. Right here is our final time, which was 0.055 seconds. And I've placed in a while loop to be less than, because the funny thing about VPython is, regardless of if you put something to be less than or less than equal to, it'll still consider this time for some random reason. I think it's just one of the quirks of this being a heavily modded version of our regular Python software. I just felt it would be important to point that out, because I know a lot of people who are currently taking 1301, CS 1301, or who have already took CS 1301 may be wondering why I didn't place an equal to sign over here. You'll see it in the data later on. Right here is the net force, which should be 0, as we're trying to maintain constant velocity. And right here in lines 58 through 60, I use the momentum principle to derive the velocity update formula and the position update formula. To be honest, the velocity update formula wasn't that necessary, considering that there is 0 net force, so the ball's final velocity will be equal to the initial velocity times 0 over something times time, which would just end up canceling everything out over on this side to be 0. So the ball's final velocity will be equal to its initial velocity. Now for the position update formula, we find our final position to be equal to our initial position plus our average velocity times our time step, delta t. For this, the average velocity will be equal to the initial velocity, which is also equal to the final velocity, which is why you may have not noticed me put v average here. Now we have a video of our computational model with a new position versus time graph and a new velocity versus time graph. As you may have noticed, the velocity versus time graph is linear and stays exactly the same throughout the entire model, and our position versus time graph represents a slope. Given that information, we now have a position versus time graph with our tracker data in comparison to the VPython model we just saw in the previous slide. Side by side, the VPython model does look like a slope, whereas the tracker model, if you look deep enough, has a few rough bumps in the edges, but it may not be that noticeable from far away. As you'll see on the next slide, tracker data doesn't perfectly model a perfect scenario of constant velocity, as the position versus time graph starts to become more shaky, whereas the computational model stays straight throughout the entire thing. Given what we just saw in the previous slide, you may be wondering, why did the computational model not match the video, or why did the video not perfectly represent constant velocity? A few potential points I could point out include that we had to place a net force on the ball initially, which in my case, for my video, was the force of my hand. Though it's small, still plays a part in our data. Also, potential forces such as air coming out of the air conditioning or heating unit may have caused the ball to experience a force such as drag force.